Okay, we are going to tackle the Biot-Savart law, and I'm going to do a bunch of examples for you. I'm going to do all of these, and the truth of the matter is, you really only need Biot-Savart for these. The rest of these you get by building from lines and rings. Okay, so what do we do? This is the Biot-Savart law. The Biot-Savart law tells you you get a small amount of magnetic field from each little piece of wire that you have. And I want to compare this with the Coulomb law, which you're probably more familiar with at this point. And this says that you get a small amount of electric field by looking at small pieces of charge. I want to point out that these are both 1 over r squared laws. They both have some silly constant in them, and they both involve the r hat direction, although Coulomb says the field points in the r hat direction, and Biot-Savart says that the field points in the dl cross r hat direction. So that's what makes Biot-Savart challenging and different than Coulomb. You have to do a cross product, and let's take a look at what we have to do in order to do that. So I'll just remind you that if you've got like a line of charge, you find the location of the piece of charge you're interested in. You look at what the r hat vector is, and your E field points in that same direction. You find some small piece of charge. Okay. With Biot-Savart, the idea is basically the same. You have dl. Now dl has a direction, though. That's the funny thing. The direction of dl is the same as the direction of the current. So you look at the current and you say dl points that way. R hat is just like it is in Coulomb's law. It points away from the piece of wire toward where the field is. Here I say the field points in the out direction. Now, how did I get that? Well, I use right-hand rule. So the right-hand rule says if you have a cross product, A cross B, okay, so for me, my A is dl, my B is r hat. You point your fingers in the direction of the first thing, dl. You point your palm in the direction of the second thing, r hat. Your thumb tells you the direction of the cross product. So that's your thumb. It points out for this particular example. Okay, so we'll use that a few times, but I'm also going to show you how to do formal cross products as well. Okay, so we'll do both examples both ways so you'll have both tools at your disposal. Okay, so let's get going. The first thing we're going to do is a line, a straight line. And in order to tackle this, we have to pick a piece of the wire. So here's my piece of wire. Here's my r hat. It points away from the line toward the point I want to find the field at. And look, I had to make some labels here. So this is X and this is Y. Okay. So I say that the field points out there. How do I know it's out? Well, I put my fingers in the direction of DL to the right. I put my palm in the direction of R hat. You might say, your palm doesn't look like it's in the direction of R hat. Okay, I agree. R hat is above. R hat is above DL, and so I point my palm up. Later, I'll show you what it looks like when R hat is below, but for now, it's above, and so my palm points up, and when I do that, my thumb points out. Okay, so from right-hand rule, I know that dB points in the out direction, and the magnitude of A cross B is the magnitude of A times the magnitude of B times the sine of the angle between them. And so that's where that sine theta comes from. Now, I don't particularly care what theta is. I care what sine of theta is. So here's theta, and that's just opposite over hypotenuse. Okay, so I can punch that in. And then if I punch in the value I have for r there, I will end up with this. So that's dB. That's what each piece of the wire contributes. And before we move on and we add them up, I want to keep my promise, and I want to show you how to do this using formal coordinates. So let's do it formally. So that is my r hat vector. So one way to think of this is give this guy a coordinate. The coordinate of this, you might say, is 0, comma, y. The coordinate of this is negative x, because it's to the left of 0, comma, 0. And if you say our vector equals the field position, 0, comma, y, minus the line position, which is negative x, comma, 0. Okay, if you subtract these, you get this. The other thing is r hat is a unit vector, so you have to divide by the magnitude, and so you end up with this extra little piece here. dl vector points, as we said, in the direction of the current, which is along the x direction, and it just has magnitude dx. It's a little tiny piece of the wire. I can do a formal cross product by setting up my 3x3 matrix and taking a determinant. Okay, so always remember dl has to go first, r hat goes second, and this guy can just get parked right out front. If I do that, I end up with this. And if I found dl cross r hat, if I divide it by r squared and put this funny little thing out front, I end up with exactly the same thing I did using right-hand rule. Some of you are going to prefer this way. Some of you are going to prefer this way. You will probably think the other one is crazy. I think it's best to do it both. Anyway, this is our contribution from either technique. The only thing left to do now is to add it. So we add up the vectors. Now, the thing to remember is that whenever you do an integral, you're really integrating from one coordinate to another. You're not integrating over a length or anything like that. So I better give some coordinates. This is the coordinate x equals negative L1. This is the coordinate x equals L2. I can do whatever I want with these. I could say it's the midpoint, but I'm just keeping it totally general. That's the integral from negative L1 to L2. If you like doing integrals, do it. It's a trig sub. It's not awful. If you don't like doing integrals, plug it into integrator.com, and integrator.com will tell you it looks something like this. This is kind of ugly. It's not particularly enlightening. What I'm going to do is I'm going to say, what happens if the wire is really long? If the wire is really long, then I can ignore this and I can ignore this because this is very big compared to that number. And then what you have is something that looks like L1 over L1 and L2 over L2. So that's 1 plus 1. This term will give a 2. And so if you look at the limit as L1 and L2 approach infinity, you end up with the field of an infinitely long wire. If this bothers you and you're like, there's no infinitely long wires, that's not true. Yeah, but if it's a pretty long wire and you stay close to it, it's infinite enough. You won't be able to tell the difference in the lab. So you may as well use the easier result. Okay, so that's our field. It points out of the page and it depends on y. But this is above the wire. What about below the wire? Well, below the wire, notice now my r hat vector points below the dl vector. And when I do that, this is what happens when r hat is below. You got to point your thumb inward. That means that this direction, z hat, is kind of problematic if I want to describe the magnetic field of the wire. Now what I'm going to do is I'm going to point the wire right at you. Okay, the wire points right at you. And so what I'm going to do is right-hand rule in various places around the wire. Boom. Here I go. DL never changes. That always points out, and so all of these hands, the fingers point out. What changes is the r hat vector for this guy points right, so the palm points right. The palm points up for this one, left for this one, and down for this one, away from the wire. When I do that, you can see that really what I have is a circle. Magnetic fields form circles around straight wires. That's pretty amazing compared to electric fields, because if you think about an electric field, we said electric fields are conservative. Electric fields from Coulomb, so I put a little s here to mean static. You'll learn later that this rule isn't quite true. But for Coulomb fields that we're familiar with, they're conservative. That can't possibly be true for B fields. They can't be zero because they always point in the same direction. And so if you add up all these contributions, there's no cancellation. They're going to add. What do they add up to? Well, if you think about it, the magnetic field, it depends on how far you are away. So if you make a circle, this never changes. That means that B can come outside of the integral and it just becomes B times L. B times L is B times the circumference of the circle. And you end up with mu naught times I. That is the cheapest derivation of Ampere's law you'll ever see. We're not going to do Ampere's law in this video. We're going to concentrate on Biot-Savart, but this is super useful for situations where you have symmetry. You can avoid all of these horrible cross products. Anyway, that's for a different video. I want to remind you of another weird thing. So in charges, we say that electric fields come from positive charges. They are born on positive charges and they disappear on negative charges. This is captured by Gauss's law. Gauss says if you draw a closed surface around it, count how many field lines come out, and you'll find that that's proportional to the amount of charge inside the surface. A way to say that locally is you won't find any new electric field lines unless there are charges around. Okay. We say that electric fields come from positive sources and they disappear into negative sinks. The situation with magnetic fields is different. Magnetic fields make circles. Think about something that makes a circle. Something that makes a circle has to return to where it started. So if you leave a surface, at some point you have to come back into it. There is no net flux through the surface. This is magnetic flux through any closed surface is zero. Sometimes people say that the flux is conserved. Locally, what we say is you can't make new magnetic field lines because there's no such thing as magnetic charge. There's zero magnetic charge. Another way to say this is no monopoles, no monopoles. Later in this video, we'll see that there is such a thing as a dipole, and they're super important. We'll put all of our fields in terms of dipoles at the very end of the video. So we say magnetic fields don't have sources and sinks. They just go around in circles with no beginning and no end. Okay, enough of that. Let's move on. So here is a ring. We saw that straight wires make circular fields. Let's see what kind of a field a circular wire makes. So I'm armed with Biot-Savart again. I do the exact same procedure. I pick a piece of the wire. I call it DL. That points in the direction of the current, which on this side points out. So R hat points that way. Let's use right hand rule first. So my fingers come out. My palm points up and to the right. And when I do that, my thumb points up and to the left. And so that's how I've drawn the arrow. I also put a right angle here just to remind you that when you take the cross product of two vectors, the resultant vector is always perpendicular. You're guaranteed to get a perpendicular vector as a result. So that's from the left side of the wire, but on the right side of the wire, the current's going in. And if I do that, then my fingers point in, my palm points away from the wire toward the field point, and now my thumb points up and to the right. So I know that these are the vectors that I'm going to have to add. In the last case, I just had one integral to do because everything pointed the same way. Here, each piece of the wire makes a contribution that points in a different direction. That means that we have to add components of these vectors. So we make x and y components of these vectors. And in principle, what we're supposed to do is add the x components in one integral and add the y components in another integral. But if you look at those x components, they're the exact same size because everyone's the same distance away, and they point in opposite directions. So we're going to save ourselves an integral and we're not going to bother with it. Instead, we're going to focus entirely on just adding up the vertical contributions from the magnetic field. So that means take the total magnitude and just do sine of theta like you would normally for any vector. So that's the vertical contribution right there. Sine of theta. So how do we get that? All right, so we know that this is a right angle, so we find a bunch of other angles. So if you call this phi, phi is 90 minus theta, but then wait a minute, that's also a right angle. So theta must also appear here again. Once you have theta, here you can put it here, you can call this theta, it's r over r again, okay? And so now we can say it's dB times r over r. We've gotten theta out of the way. So by right-hand rule, we have magnitude of dl, magnitude of r hat, r over r. I plug in for r and dl. And then if you plug in, you end up with this. And this looks like it's going to be a pretty nasty, disgusting integral. However, dl is as you go along the wire, but none of this stuff changes as you go along the wire. So when we do our integral, I can take all of that stuff outside the integral, and now I'm just doing the integral of dl. The integral of dl is L, and that's the circumference of the circle. So I just take that complicated expression and multiply by 2 pi r, and I am done. That is the magnetic field along the axis of a loop. So I'll be clear here that I'm along the axis, I'm above the center of the loop, and that's why I can say this is the same for everyone. You may say, hey, well, what happens if you go off axis? Okay, if you go off axis, things get complicated. When I say complicated, I don't mean like the physics gets any harder. I mean the integral you end up with is called an elliptic integral, and you can't do those except numerically. And so for any introductory class, you're going to stay on axis. This is not an unsolved problem in physics or anything. You do it numerically. There's a whole technique you'll learn in an upper division class called multipole expansion, which is just like a fancy kind of Taylor series, and you do the integral that way. But we're not going to concern ourselves with that in this video. I just put it there to say that we know how to do it, okay? So that's using right-hand rule. We have a result, but we haven't done it formally yet, so let's do it formally. So formally, I need to say DL points different directions in different places, so we call it the, counterclockwise direction, theta hat. It goes in the circular direction. I want to get rid of theta hat. Polar coordinates are great. The problem is the direction changes, and so if you integrate or differentiate, you have to integrate your unit vectors, which is annoying. So we're going to try and re-express everything in terms of Cartesian. So here are my x, y, and z directions. So z is up, x is out of the page, y is to the right. I want to be able to put the loop in the xy plane because things are easier to see there. Okay, so here's my theta hat direction. It's going in the clockwise direction. Part of theta hat lies along the x, and part of theta hat lies along the y. The part that goes along the x component goes like cosine of phi, and it's negative. The y component goes like sine of phi, and it's positive. But when we talk about theta, theta is this angle, and so theta and phi are complementary. So you can say this is sine of theta and cos of phi, and that's exactly how I'm going to break it up. So in the x direction, we have minus sine theta cos phi, okay? And then we can observe that r hat, so now we have r hat. So this again, same idea as before. So this is like 0, 0, z, and you can call any point down here on the xy plane. It just has coordinates x, y, 0. And so if you subtract those two, you end up with this part, and then you have to do the usual thing where you divide by the magnitude, okay? And then the last thing to do here is we want to express everything in terms of theta. Remember the x component goes like r cos theta, okay? And then the y component goes like r sine theta, okay? Now we can do our formal cross product, okay? So it's just another 3 by 3 determinant, and I've done that. I've went ahead and done that here. Okay, so you can pause if you want to go through it carefully yourself. Okay, this is how you tell a computer to do it. And then at the end of the day, what we have to do is we have to integrate these components. Now, notice I actually do have all 3 components to integrate in this case. Nothing's canceled. I'm not ignoring anything. However, I have to go all the way around the circle. So I have to go from 0 to 2 pi. The integral of cosine of theta from 0 to 2 pi, 0. The integral of sine of theta from 0 to 2 pi, 0. The integral of 1 from 0 to 2 pi is just 2 pi. In other words, everything inside that integral just gets multiplied by 2 pi. And it points in the z hat direction, just like we said it did. You might like this way, you might like the other way. I think you should know how to do both. So here's our results. We have the ring and we have the line. And this was the hardest work we're going to do in this entire video, getting these 2 results. For a line, they go in circles. For a ring, above the loop, it goes up. Below the loop, it goes down. And this should remind you of a bar magnet. A bar magnet is a north pole and a south pole. And so for that reason, we call a ring a magnetic dipole. This is the simplest structure you can make. I have a whole other video about it if you're interested. We can talk about the magnetic dipole moment of the loop. That is defined as the current going through the loop times the area vector, which points upward, and you can re-express the magnetic field in terms of the magnetic moment. We're not going to do much more with that in this particular video, but I'll rehash it again at the end. Okay, now let's greedily exploit these results to find the magnetic field of a sheet. So here I have a sheet, and if you think about what a sheet is really nothing more than a bunch of lines all next to each other. So if I know the magnetic field that a line makes, all I have to do is add the magnetic field from each of the lines. So each line is a distance r away from my point of interest. Okay, and since that's difficult to see, I'm just going to now look at the whole thing edge on. Okay, so when we talk about the theta hat direction, this is the direction, this is the angle we're talking about. I have some small amount of current on the sheet there, di, okay? And the sheet as a whole carries a current I, and I know that the small contribution due to this small amount of current is just given by my formula for a line. The theta hat direction, so we have a circle around this thing, the theta hat direction right there points down and to the left. Okay, so I'll label it just like I did before. Notice I've turned a problem about a sheet into a problem about a line. DI is nothing more than the total current divided by the area times a little bit of area, which is LDX. So we envision L pointing into the page and DX pointing along this direction. Okay, and so we have a little bit of angle stuff to do. So if I call this phi and this is 90 minus phi, I'm back to phi again, okay? And so I can break theta hat into components just like we did last time. In this case, we point down and to the left. Okay, and so I've gone ahead and I've plugged in for R as well, okay? So you can plug in for sine of phi. So sine of phi is y over r. And so that's what I punched in. Here's my y and my r. And then cos phi is x over r, and so I've plugged in x over r. So this is two integrals, and so I need to integrate over dx, and I do the same trick I did before, which is from minus L1 to positive L2. So you do that integral. Here's your integral, and again, if you like integrals, do it. They're actually not that bad. If you don't like integrals, punch it into integrator.com. If you do those integrals, you end up with something really disgusting that looks like this. And so what I'm going to do is I'm going to do the same trick I did last time. And I'm going to say, you know what? Let's just take L2 and L1 to be infinity. So now I'm going to find the magnetic field of an infinite sheet. When I plug in L2 equal infinity, right, this guy becomes pi over 2. And this guy becomes minus pi over 2. So those are going to add. You have pi over 2 minus pi over 2. And this guy, when these are infinity, you have the log of infinity over infinity, which is the log of 1. It's going to vanish. It's going to vanish. So I take L1 and L2 go to infinity, and I end up with something that looks like minus pi. So it's actually much simpler. I actually want to clean this up a little bit. So what you end up with is I wrote I over A is I over L squared. So that's like I over L. K is a symbol we often use for current per unit length. If you're like, that's weird, what's current per unit length? Well, current flows along a wire, so per unit length along the wire, I have some small amount of current always flowing there, right? This is amazing, though, because if you express it in those terms, the magnetic field is constant. It's actually constant. And this is the same issue we had before. Above the sheet, it points left. Below the sheet, for all the same reasons, it points right. If you think about it, the magnetic field is still trying to make circles. It's still trying to make circles around the sheet. It certainly can't begin or end anywhere. Okay. If this is weird, you're like, that doesn't make any sense. How could it possibly be constant? I just want to recall that when you have an infinite sheet of charge, we find the electric field from an infinite sheet as totally constant, and it flips direction just like the magnetic field flips direction for an infinite sheet. One of the things you can argue is, well, like, look, an infinite sheet, if you get farther away from an infinite sheet, you can't really tell that you're any farther away because the sheet looks the same if it's truly infinite. So perhaps it's not super surprising. All right, let's move on. Here is the field of a disk. And you might say, ugh, a disk, how do you even, what do you even do for, well, so what I'll say is, instead of talking about current, let's just plunk some charge. So there's a charge per unit area on this disk, and let's spin it at an angular speed omega. Now you build a disk out of rings. So now instead of adding up the contributions from lines, I'll add up the contribution from rings. We parameterize it. We put in some things so that we can plug things into our ring formula. And when we do that, we can say that each ring contributes whatever this is, only I replace the I with the di. That's the only change that I've made. And okay, I call the big R a little r because the different rings have different radii. The thing is, though, all of the rings, their field all points in the exact same direction. So all I have to do is a straight integral in order to do this. The weird thing is, what's di? And so if you think about it, each one of these rings carries a total amount of charge, dq. And if you wait a full period, that's the time it takes to go all the way around, that much charge will pass through your hand. If you put your hand there in that slice, all of the charge will pass through in one period. So one period is related to omega. Omega is 2 pi over the period. And so you have a period in the denominator, and that ends up putting a 2 pi over omega in the top. And so anyway, all of this is simplifiable to your di is just sigma times 2 pi r dr. That's what dq is. And then t is 2 pi over omega, so that you can think of the 2 pi's as canceling. And you end up with that omega there. Okay. So I can plug that back in here, and then all we have to do is integrate over the disk. And here we're integrating over R. So my smallest ring starts here. My biggest ring goes all the way out here. The geometry here is loads easier because I've already done the hard stuff by working these two guys out. Okay, you can do that integral if you like, or plug it into a calculator. You end up with a magnetic field that looks like this. Okay, so this is the result for the magnetic field from a disk that is spinning. Okay, so what do we do from here? Well, now we find the magnetic field from a shell. So this is a hollow sphere that has same thing as before, some surface charge density, and it's spinning the same way as the other one was. So what's this made of? It's made of rings, just like the disk was made of rings. Only these rings go like this. Okay, so how do I find it in this case? So in this case, I can say that my rings have different radii. The radii of each ring is r sine theta. Each ring is a distance from the center, r cos theta. The distance from the center of the whole sphere is d, and the distance from the ring, which is the thing I'm finding the field of, to my field point is z. So I can say that the field of each ring is, steal this result, and then I can say that di, same thing we did last time, dq over t, only in this case, my dq is, you can imagine this ring has some small amount of thickness here. There's some small amount of thickness here. So you have a tiny little ribbon of current that is rotating around. So there's that. And then rd theta is the height of each ribbon. So that's this piece here. Okay. And then omega over 2 pi instead of 1 over the period. Okay. So I also have the r value is r sine theta. And then z, the distance from the hoop, to my field point in terms of the distance from the center of the sphere looks like this. So if I plug all of that in, it looks truly horrendous. This looks like it's going to be an awful integral. And it is, but honestly, it's not your problem. You plug it into an online integrator, and when you do, it'll give you one of two results. It'll give you this, or it will give you this. And you might say, wait a minute, how could you possibly get two different results? Well, when you integrate, you end up with something that looks like d minus r in absolute value. And it's your choice. Is d greater than r? Then this becomes d minus r. Is d less than r? In which case this becomes r minus d. Depending upon which choice you pick, the algebra will shake out a little differently. I don't want to do any more algebra in this video, so I'm going to leave it there and see if you can work out those results yourself. The point I'm making is the formula for the field looks different outside than it does inside. Okay, so this is now our result for outside along the axis. Last one, the most complicated shape, is by far the easiest one to do. What we're going to do now is we're going to steal our result from a shell and use it to build the sphere. So a sphere is made from just a bunch of shells. Each shell, we know, makes a magnetic field that points upward. Take d to be the same d. Every single shell is the same distance from the field point I'm looking at. So I can just say that the magnetic field from each shell is, I steal my result from last time, sigma, the charge per unit area, is the charge per unit volume times a little bit of length. That's what gives you charge per unit area. Okay, so all that's left to do is to write this down and integrate. My smallest shell has a radius of 0. My biggest shell has a radius of r. And if you do this, you'll end up with this as the sphere. Notice that this is along the axis and it is directional. If you go off axis, it doesn't point in the z-hat direction anymore. It will. I'll tell you a little secret. It looks just like a bar magnet if you put iron filings around it. Okay, so for a line and a sheet, these are my results. This is interesting because it makes circles, and from this we conclude no monopoles, which is fascinating. A sheet is interesting because for an infinite sheet, you get a constant magnetic field just like you get a constant electric field. And then for all of my curly guys, the ring, the disk, the shell, and the sphere, all along the axis, because we can't go off axis, you end up with things that, I don't know, they're kind of ugly. But I want to show you something that's rather beautiful. If you express all of these in terms of the magnetic moments of each of these objects, they are all the exact same formula. If you get far away from any of these shapes, they all make the same formula, and in some sense, this is like a Coulomb's law for magnetism. There's no such thing as a monopole. There are things called dipoles, and the field of a dipole is what you are looking at right now. And so there's a whole technique where you can just build any shape you want out of assembling the dipole moments that are hiding inside of that shape. That is definitely much more than we're going to conquer here, but something to think about. Okay, hopefully this video was more helpful than confusing.